let's test you on some of this stuff. If you don't have any good stuff to go over, then I'll test you on certain things. And the only reason I say that is because I have another calculus student, and I went over there the other night thinking I knew exactly what she was going to be doing, and she was on totally something different. Okay. Let's start with an easy one. What's that the equation of? What is that the equation of?
What do you mean?
It's the equation of a circle.
Oh, yeah.
Okay. So if I wanted to differentiate this, the left side with respect to x, in other words, I want to do that. I can do that as long as I do the right side also. Do the left side. In other words, there's one thing I know you're going to have to know, and that's implicit differentiation. So let's cover it until you understand it. How do I implicitly differentiate this? In other words, it's called implicit because I don't have y defined. If I had y equals something, a function of x, then I would use explicit differentiation. But in this case, I have to use implicit. So how do you implicitly differentiate that?
I don't know.
Okay. Well, when we come to a variable that's the same as our denominator, x, then I can just do that. In other words, I can just apply the power rule. When we come to a variable that is not x, like y, then I can differentiate the outside like that, but I have to follow it by a dy dx. In other words, anytime I run across a variable that is not, in this case, x, it could be t, r, whatever, I've got to follow it by this thing. It's the derivative of the right side. It's the derivative of a constant.
0.
Okay. Now solve that equation. Remember what our goal here is to solve for dy dx. So what's dy dx going to be equal to? In other words, isolate that. Solve it just like it was a variable, a different variable, and you're solving an equation. Get rid of everything else.
When I subtract by 2x and then divide by 2y?
You got it. That is dy dx. And of course, I can simplify that a little bit. So it's minus x over y. Now, we are looking at a circle of radius 5, right? That's what that is the equation of. And what we're saying is that the slope is a function of both x and y. So if I said to you, what is the slope at this point right there, which is 0, 5, tell me what it is. In other words, I can see the slope of the tangent line would be that, but let's use this equation. Plug in the point. In other words, that's the x-coordinate, that's the y-coordinate. And our derivative is a function of both x and y. So plug it in. What do you get?
0.
That's the slope of that tangent line. Okay? Now, plug in this point, which is minus 4, 3. That point right there.
It would be negative 4/3.
Well, first of all, look at it. Is that a positive tangent line slope or a negative?
That's positive.
Okay.
Oh, yeah, because the negative inverses, so it'd just be 4/3.
Exactly. And that is the slope of the tangent line right there. Now, if I wanted to know the slope of the tangent line right there, you see where I'm drawing? And that's at the point 5, 0. What do you get then?
I don't know.
Plug it in. What do you get after you plug it in?
Would it be 8/3 plus 8/3? So
Hold on. This is our point right there. This is our slope. Minus x over y. Plug it in. The 5 in for x and the 0 in for y. What do you get?
0.
Nope. What do you get? Give it to me before you simplify it. There you go. You get minus 5 divided by 0, right? And we know that that is undefined slope. In other words, you can't divide by 0. And we also know a vertical line is an undefined slope. It's basically an infinite slope. Okay? So when I check this point here, I would expect the slope to be undefined, and it is. And if I check this point over here, the slope, that point is negative 5, 0. You're still going to have 5 divided by 0, which is still undefined, and you still have a vertical slope. Okay? Now, the one thing quite different about implicit differentiation relative to explicit is that with implicit, you generally end up with your answer in terms of both x and y, not just x, which is usually what you get when you explicitly differentiate something. Now, I'm going to pull some problems out of the book here. Remember what the rule is. As long as you're explicitly differentiating, or rather, when you're implicitly differentiating, I want you to differentiate this. Hold on a second. In other words, implicit differentiation allows you to differentiate everything. Notice that I can't really solve this for y very easily. That'd be really hard to solve for y. So I'm not going to have much luck solving this for y and then explicitly differentiating. And you get an awful lot of functions like that. And implicit differentiation is probably more important than explicit. In terms of solving real-life problems, implicit differentiation is what you usually use. So if I'm implicitly differentiating the left side, I'm doing that, and I'm doing it with regards to x. I got to do the same to the right side. Now, term by term, what is the left side? Remember, as long as I'm dealing with a variable that's the same as my denominator, x, then I just apply the power rule, nothing else.
Sorry about that. Just had to close my door.
So what's the first term going to be?
X to the fourth power.
Apply the power rule to that first term.
4x to 2 cubed.
Okay. Now we got to deal with this term here. What rule do we have to use to deal with that?
I don't know like what to call it, but is it the product rule?
Two things are being multiplied together, it's the product. Okay, so let's apply the product rule to that. Here, let me put it in parentheses so we'll know that it's got a couple of terms there. How do I apply the product rule to that?
So it'd be 2x.
Now, always start with the first term, please. Just because I know what you're doing when you do it. I understand you can do it the other way. But there's a real straightforward, easy way to do it. The product rule, just start with the first term. Okay? Now, take the derivative of the second term.
So it'd be 2y.
And because it's something different than x, I have to follow it with dy dx. That's the rule. Okay? What's the rest of the product rule?
And then you have 2x times y squared dy dx.
Okay, the y squared is correct, but we weren't taking the derivative of y, were we? We took the derivative of the x squared times y squared. So we don't have to follow that with a dy dx. We only have to follow that with a dy dx if we're differentiating the y term. And the second half of this, we weren't. The first half we did. But the second half, in other words, this was u v prime plus u prime v. And you know what I mean when I say that, right?
Yeah.
Okay, you hesitated a little bit there. If y equals uv, what does y prime equal?
U v prime plus u prime v.
Yeah, and that's what we did here. We did u, and we did it in this order. Now, I understand that you could do it in the other order. In other words, you could do it the way you were starting to do it. It's just, I think it makes sense to always do it in the same order. It's easier to remember. In other words, if you always start with u, which is what I want you to do, I don't want you to start with this part. I don't want you to start with u prime. Always start with u, and then figure out v prime, and then, in other words, don't do it that way. Do it this way. All right? We're not done. So all we did was that middle term. Let's do this term. What's that going to become?
Just 2y.
Minus 2y. And in this case, we are differentiating y. So I have to follow it with a dy dx. Remember that rule.
And when you differentiate, it's only when you differentiate y too. It's not when you differentiate x.
Exactly. And the reason is that when we differentiate x, it's the same as our denominator, the dx. So we explicitly differentiate it. But when we run into a variable that is not x, then we have to follow it. If we're differentiating that, we have to follow it with a dy dx. Okay? And this is all equal to 0. The right side is 0. And now here it gets a little tricky. Remember what our goal is. We're trying to solve for dy dx. What I have in the circle on the left is what we have. How are we going to solve that for dy dx?
I'm still a little confused, so I don't know.
Well, this just is an algebra problem at this point. In other words, we have an equation here, and we're trying to solve for dy dx. We're going to gather all like terms that have a dy dx in them on the left side of the equation, per this. This is always the way you do these. And this is always the toughest step, is this step. The rest is just plugging and solving. This requires a little bit of algebra. Okay? So on the left side, I put every term that has a dy dx in it, which is this term and that term. On the right side, I put everything else. Everything else. So I've got minus 4x cubed plus that, plus 2xy squared.
Wait, why is it minus?
Because I had to move the 4x cubed to the other side of the equation.
Oh, yeah, okay.
This should
Wait, why is it?
And this should be minus also. Thank you. You pointed out a mistake that I had made. Okay. Now, that equation's the same as that equation. It's just I've rearranged stuff. You with me?
Yeah.
Okay. Now how do you solve for dy dx?
So you want to get dy dx just by itself.
Exactly.
So you can divide by 2y because that's in both terms.
Yeah, you don't need to do that yet. That's not the issue here. And that, yeah, you can't really, well, you could, but let's not worry about that for a moment. We'll simplify it when we get done. The crux of this is factoring out the dy dx. You see why that's going to allow us to solve it? When you factor out the dy dx, you're left with all of this.
That's definitely the better route to go because it's in both terms. So.
Well, and now I can divide both sides by what I have in the parentheses here. And that's dy dx. Since I've divided both sides by it, that's what I get. In other words, that is dy dx. Now, I can simplify that a little bit. I can divide top and bottom by 2. That's the only thing I think I can do. If I divide the top by 2, that becomes 2, that becomes 1, that becomes 1, and that becomes 1. So my final answer for y prime, which is dy dx, upper right here, is going to be minus 2x cubed minus xy squared all over x squared y minus y. Now, that's the correct answer. Ooh, hold on a second. I'm looking at the book. Yeah, it actually is. I could do some simplification by dividing by -1. I could change most of those negative signs you're looking at to positive signs, but that's not really required. And there's no other really way to simplify it. You could do some factoring. I could factor out an x from the numerator and a y from the denominator. But notice that doesn't allow you to do anything else. You can't really do anything in the way of simplification just by factoring. And that's kind of the rule I use for when you should factor and when you shouldn't. If you can't simplify it further, don't factor. No need for it. Okay? Now, the real life problems I apologize, I hate this program. All right, getting a new page is difficult. Let's take that same function. Okay. Oops, that was a minus. Y squared equals 0. This time, I want to solve for the derivative of the left side of the equation, only this time I'm going to solve it relative to a variable called t, which is quite common in calculus. T is usually time. In other words, an awful lot of calculus problems, you want to know what the derivative is relative to time, because that's like the speed. If you're talking the velocity of something, you're talking dx dt. Okay? If you're talking about beach erosion, you're talking about dx dt. So many things are relative to time. So now let's do this problem, only instead of differentiating it relative to x, we're going to differentiate it relative to t. So what's my first term?
4x
Cubed. Because x is not t, what do I have to follow that with?
d over dt.
dx over dt.
Okay.
Okay? In other words, the rule is very simple. When you run into a variable that is not the denominator variable, you have to follow it with the d of the variable you ran into divided by the d of the variable that's in the denominator. Okay? Now, do this part again using the product rule.
So then you'd have x squared 2y, and then would that be dy over dt?
You got it. Plus what?
2x over dx over dt.
Hold on. 2x dx dt, because I was differentiating the x variable, times what?
Times y squared.
Okay. And finally, and notice I did not have to follow that with a dy dt because I wasn't differentiating y. I was only differentiating the x. And then the last part is what?
2y.
dy dt. You see why I have to follow that by a dy dt?
Yeah.
Okay. Now, because I was differentiating with respect to a variable that was not in the equation, then I'm going to get an answer that's got some dx dt's in it, some dy dt's, some more dx dt's, and some more dy dt's. So I can't really solve for anything unless you give me some of these answers. Now, let's do a real problem where you can understand related rates. We have a ladder, 5 feet tall. The information we're given is that the bottom of the ladder is moving in that direction at 2 feet per second. Got it? In other words, this ladder is sliding down the wall. So the bottom of it is moving to the left at 2 feet per second. And the question is, what's the top of the ladder doing? It's obviously going down. Well, first of all, when I say that the bottom of the ladder is moving to the left at 2 feet per second, 2 feet per second is a velocity. That means it's a derivative. So that's what dx dt is equal to. 2 feet per second. You with me?
Mm-hmm.
This is one of the simpler related rate problems. But this is where you really see the advantage of implicit differentiation. And their question is, what is dy dt? They want to know what the top of the ladder is doing. And so that's what we're looking for. And we want to know it. It's not always the same. In other words, at a certain moment of time, when that measurement is 3 and when that measurement is 4, that's when we want to know it. In other words, when the x-coordinate is exactly at -3 and the y-coordinate is at +4, what is dy dt? Okay? So the way we solve this, in other words, it's not obvious at all. You would have no way of solving this without calculus. Impossible. You see why? And do you see why it's called related rates? Because we know one rate. We know the rate that x is changing, and we're trying to figure out the rate that y is changing. And we're trying to do it at a very, very specific moment in time. The moment in time when the bottom of the ladder is exactly 3 feet away from the wall and the top of the ladder is exactly 4 feet away from the wall. Remember what velocities are. They're instantaneous. In other words, the x dimension is changing by 2 feet per second, but only when that x dimension is exactly where it's at. When the ladder gets to this point, the x might not be changing at 2 feet per second anymore. It's a different spot. And it changes. As the ladder falls down, the speed that the bottom is going changes. Okay? So the way we start is give me an equation that describes this situation. That is a right triangle, right? What do we know about right triangles? Pythagorean Theorem say.
Yeah. So what does that have to do with the rest of the problem, though?
I'll show you. What's the Pythagorean Theorem say here?
A squared plus b squared equals c squared.
Okay. So a squared in our case is x squared plus y squared equals, well, a ladder doesn't change its dimension as it falls. It's always 5 squared. So that's the equation we're dealing with for this model. Now, implicitly differentiate this with respect to time. In other words, take the derivative of the left side with respect to t and take the derivative of the right side with respect to t. What do you get on the left side?
You get 2x d of x over dt plus y squared.
No. We have to differentiate that with respect to t also.
Oh, yeah, my bad. I don't know why. I just felt like they're in the same term, but they're not. No. So just be 2y dy over dt.
Okay. And that's equal to 0. Okay. Now, we're given this. We know what that is, 2 feet per second. And they're saying, what is dy dt when x is 3 and y is 4? Notice that I'm going to fill in every variable except dy dt, and I will be able to calculate dy dt. So I'm going to plug in the x equals 3, so I have 2 times 3. dx dt is 2 feet per second, plus 2 times y, well, y is 4 at this precise moment in time, times dy dt. That's all equal to 0. Okay? And what that gives you is dy dt is going to be equal to minus 12 divided by 8, or minus 3/2. That's the speed that the top of the ladder is going. Now, why is it negative? That is dy dt, which is what the problem wanted to figure out. Why is it negative? Why was the dx dt a positive?
Because they're both decreasing and increasing?
No, the x is increasing, right? In other words, the only thing that determines whether this should be a positive or negative is if the x is changing, if it's increasing. It's not the fact that it's going to the left. That's not the reason that would be negative. The fact is that x is increasing at a rate of 2 feet per second. Notice where I've drawn my dotted line. In other words, in another moment, that's where the ladder is going to be. And x will no longer be at the point 3. X won't be 3 feet anymore, because it will have slid down further. Now, the reason that y is negative is, notice that y is decreasing, the y measurement. In other words, right now, at this particular moment, y was 4 feet, but in a half a second, it's going to be less than 4 feet, right? Right?
Mm-hmm.
In other words, as this ladder slides, the y dimension gets smaller. It decreases. Therefore, dy dt should be negative. And it is, minus 3/2. So even though the x-coordinate is growing by 2 feet per second, the y-coordinate is declining by 3/2 feet per second. And notice what I had to do to solve this problem. I had to figure out the equation that fit this model, in other words, the Pythagorean Theorem. Then I had to figure out that I had to differentiate both sides relative to time. And the reason is because they gave me dy or dx dt, and they wanted dy dt. Clearly, we have to differentiate with respect to time. It wouldn't do me any good to differentiate this with respect to x or with respect to y. I gotta differentiate it with respect to time because that's the information they gave us. They gave me dx dt. When they said the ladder was sliding at 2 feet per second, that's its velocity. A velocity is a rate, and a velocity is a derivative. Whenever you see the words rate or derivative, especially if it's relative to time, and most of these problems are, it's that derivative. That's what that means. The velocity at the bottom of the ladder is 2 feet per second, and it's getting bigger at 2 feet per second. Question is what's the velocity of the ladder, or the height of it doing? Now, clearly, when the ladder falls all the way down, like that, it would be 5 feet from the wall. What's dx dt at that point in time? How fast is the base increasing when the ladder is fallen all the way to the floor?
Not at all.
So dx dt would be 0 when x is 5. What's dy dt at that point in time?
It would also be 0.
Exactly. So you can see that the speeds vary depending on what point in time you want to measure it. So that's why I was interested in the point x equal 3, y equal 4, because now I can plug it into this equation down here, and now I've plugged in 3 of the 4 variables, and I can solve for the 4th, which is dy dt. And that is probably the best example to explain related rates and implicit differentiation. Now, there is a classic one, and I'd like to do that and see if you can do it. It's the classic one where you have a police car and it's chasing some bank robbers. Bank robbers are going that direction. The police car is going in that direction. Police car knows the speed it's going, 60 miles per hour, but it doesn't know how fast the robbers are going. But it does have a radar on board the police car, and so it can figure out how fast the robbers are moving away from the police car. Now, this police car has to go down to this intersection, turn left, and start chasing the robbers, okay? But the only pieces of information the police car has is its own speed heading into the intersection, and it can tell that this speed is 20 miles per hour. In other words, it looks at its radar gun, and it sees that the car is moving away from the police car at 20 miles per hour at a particular point in time. And we'll call that point in time when it's 6 miles away from the intersection and the robbers are 8 miles away from the intersection. So, give me the equation that fits this model. Now, excuse me. Let's start with the givens. They gave us dy dt. What is dy dt?
60.
Positive or negative?
Negative.
Correct.
No. Oh, yeah.
Right. They're getting closer and closer to that intersection. So this distance, the y distance, is decreasing as they go to the intersection. Now, what else did they give us? dz dt. The distance between the cop car and the robber car. What's that?
20.
Positive or negative?
Negative.
Is it increasing or decreasing?
Decreasing.
Not yet. As long as that cop car is headed south towards the intersection, it's not making up any time on this robber car. The robber car is going due east. We're still going due south. It has to be getting increasing at 20 miles per hour when, and this is always critical, when y is equal to 6 and x is equal to 8. In other words, I'm giving you 4 pieces of information, and what I want to know is how fast the robber car is going. I want to know dx dt. Notice I have no way of figuring that out other than with calculus. I have any idea how fast the robber car is going. The only thing I know is it's separating from the police car at 20 miles per hour at this moment in time when the police car is exactly 6 miles from the intersection and the robber car is exactly 8 miles from the intersection. So dx dt is what we're trying to solve for. Okay? Now, let's set up a master equation that fits this model. It's a right triangle. What's the master equation?
Would it be,
Now, here we have a variable. In our ladder problem, the ladder was 5 feet in length. But that's it. It didn't change length as it fell. It always was 5 feet. This, the hypotenuse is changing length as the cop car goes south and the robber car goes east. So I need an equation that is variable. In other words, it's x squared plus y squared equals what?
c squared.
Well, let's use
C squared.
Let's use z. C is when you use a and b. If you're going to use x and y, then the hypotenuse should probably be z. Okay? Now, what have they given us? They've given us dy dt. They've given us dz dt. What do we have to implicitly differentiate everything by? By dt, right?
Mm-hmm.
In other words, I want to differentiate the left side, but I want to do it relative to dt. I want to differentiate the right side, and I want to do it relative to dt. Even though there's no t in this equation, doesn't matter. Everything they gave us was in terms of dt. Some dy over dt or dz over dt, whatever. So let's differentiate that. I'm going to be scarce on my room here. So
Would it be
differentiate the left side implicitly.
would it be negative 60x squared?
Hold on. No, just differentiate it based on these variables. Don't fill in anything yet. You have to implicitly differentiate the function first. So, what's that?
What do you mean, what's that?
Differentiate the left side of this equation.
Oh, it would be 2x. Yeah.
What's the rest of it?
dx over dt.
Good.
Plus 2y dy over dt.
Good. Equals. This one isn't zero because we're not dealing with a constant. We're dealing with a variable, z.
Yeah, so just be 2z dz over dt.
Okay. Now, every unknown in there I have. I've got dy dt, I got dz dt, I know that it occurs when x is 8 and y is 6. The only thing I do not know is dx dt. Everything else I know. So when I fill in everything else, I'm going to be able to solve for dx dt, which is the speed of the robber car. So how do I do that? How do I solve this for dx dt? Give me the next line. 2 times.
Subtract.
Hold on.
By.
Just substitute at this point. In other words, we now have an equation that has 3 variables and 3 derivatives. Excuse me. We have, yeah, we do. Okay, so we have to substitute for everything. What's the x measurement at this point in time that we're going to figure out what dx is? It's 8, okay. We don't know dx dt, that's what we're trying to solve for. But what's the y measurement at this point in time?
6.
And what's dy dt? What's the speed of the car?
Negative 60.
Good. And it's equal to, what is z? If y is 6 and x is 8, what is z going to be at that moment in time? You just need a little algebra for that. That's a 3, 4, 5 triangle. So what is z?
That would be
not dz dt, but what is z? In other words, what is this measurement when y is 6 and x is 8?
So it would be 36.
It's a 3, 4, 5 triangle. This is a 6, 8, what kind of triangle? 6, 8, 10. In other words, the z measurement is 10 when y is 6 and x is 8. If I gave you a triangle, a right triangle, and I said this is 6 and this is 8, tell me what the hypotenuse is, you'd figure out, and it was 10. Okay, that's all you're doing. So z is 10. So now I know what to substitute for z. And then what's dz dt? It's one of the givens.
20.
Okay, and it's a positive 20 because that is separating from that police car at the moment. Now once the police car hits the intersection and starts chasing it, it may gain on it, it may not. We don't know yet what the speed of the robber car is. If the robber car is going 70 miles an hour, then it's not ever going to catch it unless it speeds up, the police car. But first of all, it's got to get to the intersection. Okay, so if I do this math, what do I get? Let me see if I can do this math real quick. I get 16 dx dt minus 720 equals 400. That's what I get when I solve that. In other words, all I'm doing is simplifying that, simplifying that, simplifying that. Now I want to solve for dx dt. So let's move the 720 over to the other side. Makes it 1120. Now divide by 16 and we have our answer. We have dx dt is equal to 1120 divided by 16. I have a calculator here. Let me do that real quick. 1120 divided by 16. I'm curious as, it's going 70 miles an hour. Robber car is. Okay. So the answer to the question is dx dt is equal to 70 miles per hour. and it's a positive. In other words, this robber car is definitely moving east. It is separating itself from the intersection at 70 miles an hour, so x is increasing. That's the x measurement right there. Since the robber car is moving to the right at 70 miles an hour, it's a positive. Now, the cop car, having done the calculus and figuring out what the robber car's speed is, it knows it's got to accelerate a little bit. It's got to get to the intersection, and then it's got to hightail it after that robber car at some speed greater than 70 miles an hour, otherwise it's not going to catch it. This problem for me was the light bulb moment of related rates. I did not understand related rates until I got to this problem. And then the light went on. And so this is my favorite related rate problem because all three dimensions are variables. Whereas the ladder was a 5-foot ladder, so the only thing that was changing was the x dimension and the y dimension. But in this model, the x, the y, and the z are all changing. So, and when you figure out a speed, it's always an instantaneous speed. In other words, the robber car is going 70 miles per hour at the moment when the cop car is exactly 6 miles from the intersection and the robber car is 8 miles from the intersection. In another 500 yards, it might not be going that speed anymore. But at that moment, that's what calculus is all about, is instantaneous. It's at a given moment what is speed, or what is the velocity. And so this technique, and notice that once we came up with our equation, which was x squared plus y squared equals z squared, well, the only thing I could do was implicitly differentiate that. I have no way to explicitly differentiate it. And so you have to implicitly. And that's generally what you have to do with all related rate problems, is implicit differentiation, almost always with respect to t. But you can always figure out with respect to what variable by the information they give you. In other words, by the fact they told us what the cop car's speed was, we knew they were giving us dy dt. Speed, or velocity rather, is dy dt or dx dt or dz dt. It's always relative to time. That's why it's miles per hour. It's not dy dx. It's not the derivative of y relative to x. It's relative to time. And all velocity is that. And that's why time is so critical in most calculus problems. And most implicit differentiation, you're going to be differentiating with regards to a variable that's not even in the original equation. My original equation was x squared plus y squared equals z squared. Well, there's no t in that. But because the information they gave us was a velocity which was dy dt, now I know what I have to differentiate with respect to. And these problems can get hard, really hard. Yeah, we don't have enough time to do another one, so that would be a good place to stop. But there are two problems that show you the value of implicit differentiation. You haven't really had a problem yet that showed you the value of explicit, but clearly these last two problems, the ladder problem and the cop car problem, they were terrific problems for answering questions that we would have had no other way to answer. We don't know what the speed of that robber car is when we're looking at it. Because even though I'm pointing a radar gun at it, the radar gun is only giving me the separation speed between the cop car and the robber car. It's not giving me the speed of the robber car. Now, if I'm at the intersection and I'm pointing my radar gun at the robber car, then I would know it was going 70 miles an hour. But I'm not. I don't have any device that allows me to know the speed of that robber car other than calculus.
I got you, yeah.
Okay, and there's literally thousands of problems like this where you have to do it this way.
Okay, well, these are actually pretty interesting too. Do you know if there's any place I could like find to like practice these?
You have a textbook at all?
Yeah, I do.
What's your textbook?
It's the calculus
Of
AP.
Of a Single Variable by Larson, Hostetler, and Edwards?
No, it's by Briggs, Cochran, Gillett.
Okay. Go in there and look up related rates.
Okay.
You'll see a ton of problems.
Okay.
And
cool.
Furthermore, in that chapter, they'll show you some examples. And you may have to look at a few more examples before you really catch on.
Okay, cool.
One of the more difficult subjects of calculus is related rates.
Mm-hmm.
So just find the section in the book that talks about related rates. It should come relatively shortly after they talk about implicit differentiation. Okay?
Okay.
Because the main purpose of implicit differentiation is to solve related rate problems. So that's where it's going to be. And it might be a chapter later or a half a chapter later. I don't know. They stick a lot of stuff in between it. But that's... You'll certainly get practice problems when your teacher gets to this area, and hopefully you'll have a little bit of a head start on it now. Okay, Jacob,
Cool.
I got 8 o'clock, so I got to run.
All right, well, you have a good night.
You too. I'll talk to you Thursday.
All right, bye.